November 13th, 1942. 30,000 feet above the California desert, Lieutenant Harold Comstock rolls his P-47 Thunderbolt inverted and pulls the stick forward. The massive fighter drops into a vertical dive, her Pratt & Whitney double Wasp engine screaming at full power. Within seconds, the airspeed indicator needle sweeps past 400 miles per hour, then 450. 500. The needle slams against the stop at 700, but Comstock knows he's going faster, much faster. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Then it happens. The control stick freezes solid in his hands. Not stiff, not heavy, completely frozen, as if welded to the cockpit floor. The elevators, those critical tail surfaces that let him pull out of the dive, are locked by forces no human can overcome. 28,000 feet. 25,000. The ground rushes up at a rate that makes his stomach curl, that pushes his body back against the armor plate like an invisible hand trying to tear him from the aircraft. Comstock knows what's supposed to happen next. He's seen the wreckage of P-47s that dove straight into the desert floor, pilots unable to recover, unable to do anything but ride 7 tons of fighter aircraft into the ground at terminal velocity. His hand finds the trim wheel. Not the control stick. That's useless now. The small crank that adjusts the elevator trim tabs. He rolls it back, 1 click, 2 clicks, fighting against buffeting so violent his vision blurs. The aircraft shudders like it's tearing itself apart. 20,000 feet, 18,000. Then, below 15,000 feet, something changes. The airspeed is still insane, still beyond anything the aircraft was designed for. But the stick moves. Just slightly at first, then more. The trim tabs have done their job, applying pressure where the elevators themselves couldn't. Comstock pulls, gently, fighting every instinct to haul back hard. The P-47 groans, structural frames flexing under G-loads that would snap a lighter aircraft in half. The horizon comes up, levels out. He recovers at 12,000 feet with bruises across his chest, from where the harness dug into his flesh, and a story that nobody outside Republic Aviation will believe for decades. What Comstock had just survived wasn't an equipment failure or pilot error. He'd encountered the edge of human flight, the invisible wall where the rules of aerodynamics shatter and reform into something terrifying and new. In 1942, it had a name that sounded almost quaint. Compressibility, the phenomenon that was killing test pilots, combat flyers, and anyone who pushed the newest generation of fighters past 500 miles per hour in a dive. But here's what nobody understood yet. The P-47 shouldn't have been able to recover at all. At those speeds, approaching the sound barrier itself, most aircraft of the era simply disintegrated, control surfaces ripped off, wings buckled, pilots died without ever knowing what killed them. Yet, Comstock lived. Roger Dyer, flying with him that day, lived. Over the next 3 years, hundreds of P-47 pilots would push their aircraft into dives that exceeded 550 miles per hour and pull out alive. This shouldn't have been possible, and the reason it was possible traced back to one man's refusal to accept what every other aircraft designer in America believed was impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The man's name was Alexander Kartveli, though almost nobody outside aviation circles remembers him today. Born Alexander Kartvelishvili in Tbilisi, Georgia, in 1896, he'd fled the Bolshevik Revolution to study in aviation engineering in Paris during the 1920s. One of his early designs set a world speed record. When American entrepreneur Charles Levine brought him to New York in 1927, Kartveli arrived as a penniless immigrant with a head full of ideas about how aircraft should be built and an obsessive attention to the problems nobody else was solving. By 1939, he was chief engineer at Republic Aviation, the company that had evolved from Alexander de Seversky's struggling aircraft firm. Kartveli had a reputation. He didn't design pretty airplanes. He designed aircraft that worked, that pushed boundaries, that solved problems other designers claimed were unsolvable. When the Army Air Corps came to Republic in 1940 with new fighter requirements, those requirements seemed almost designed to produce failure. The military wanted a fighter that could reach 400 miles per hour at 25,000 feet. It needed 850 caliber machine guns, more firepower than any fighter then flying. It required armor plating to protect the pilot, self-sealing fuel tanks to survive combat damage, and at least 315 gallons of internal fuel for extended missions. Every engineering calculation said these requirements were contradictory. You couldn't have that much firepower, that much protection, that much fuel, and still achieve the speed and altitude performance the Air Corps demanded. The aircraft would be too heavy, the engine would lack sufficient power. The whole concept violated every principle of fighter design that said speed came from lightness, from stripping away everything non-essential. Kartveli looked at the requirements and saw something nobody else did. He saw an opportunity. On June 12, 1940, he submitted a proposal that made other designers think he'd lost his mind. His fighter would weigh nearly 13,000 pounds, twice the weight of the fighters then in service. It would be powered by the largest, most powerful engine available, the Pratt & Whitney R2800 Double Wasp, a massive 18-cylinder radial producing 2,000 horsepower. That engine would be turbo-supercharged, using exhaust gases to compress intake air, maintaining full power at altitudes where other fighters gasped for oxygen. The catch was size. To fit the turbo-supercharger system, to accommodate all that fuel, all those guns, all that armor, Kartveli's fighter would be enormous. The fuselage would be nearly as large as a medium bomber. The wingspan would exceed 40 feet. The profile would resemble, as British pilots later joked, a milk jug with wings, hence the nickname that stuck, the Jug. The Army Air Corps, desperate for any solution, ordered a prototype. On May 6, 1941, test pilot Lowry Brabham took the P-47B into the air for the first time. The aircraft performed beyond expectations, reaching 412 miles per hour in level flight, climbing to 15,000 feet in 5 minutes. But it had problems. Serious problems. And one of those problems would nearly kill the entire program. At high speeds, the control surfaces became impossibly heavy. Pilots reported that above 400 miles per hour, moving the ailerons required strength beyond normal human capability. The stick forces weren't just high, they were dangerous. In a dive, when speed built rapidly, the elevators locked up completely. The fabric covering on those control surfaces ballooned and sometimes ripped apart as trapped air expanded in the thin atmosphere above 30,000 feet. The solution to the fabric problem was obvious. Switch to all-metal control surfaces. Republic engineers did that, and the surfaces stopped disintegrating. But the control forces remained brutal, and something far worse began emerging from test flights. The P-47 could dive faster than any fighter ever built, much faster. When a 7-ton aircraft with a 2,000 horsepower engine pointed its nose at the ground, acceleration was violent and immediate. Terminal velocity, the speed where drag finally balanced gravitational pull, exceeded 600 miles per hour. Pilots were encountering speeds that approached the sound barrier itself, and at those speeds, the laws of flight changed in ways nobody fully understood. Compressibility wasn't just a technical term, it was a death sentence. As an aircraft approaches the speed of sound, roughly 760 miles per hour at sea level, airflow over the wings begins behaving strangely. Instead of smooth flow, shock waves form. These shock waves create tremendous drag, alter the center of pressure, and most critically, render control surfaces nearly useless. The elevator loses effectiveness right when the pilot needs it most. The aircraft develops what pilots called Machtuck, a nose-down pitching moment that steepens the dive and increases speed even further. Multiple P-38 Lightnings, Lockheed's twin-engine fighter, had flown straight into the ground when pilots encountered compressibility and couldn't recover. The P-38 was faster than most fighters but lighter than the P-47. If the Lightning couldn't survive compressibility, how could the massive Thunderbolt? This wasn't theoretical. This was pilots dying. The very capability that made the P-47 potentially valuable, its incredible dive speed, might make it unusable in combat. German fighters like the Messerschmitt Bf 109 and Focke-Wulf FW-190 could outturn American fighters at low and medium altitudes. The counter-tactic for American pilots was boom and zoom. Dive from altitude, use superior speed to attack, then zoom back up before the enemy could respond. But if American pilots couldn't survive the dive itself, the tactic became suicide. Republic aviation engineers knew they had a crisis. The P-47's first combat deployment was scheduled for early 1943. The Army Air Corps needed these aircraft desperately. The bomber offensive over Europe was suffering horrific losses. B-17 and B-24 bombers were being slaughtered by German fighters, and the only solution was long-range escort fighters that could protect the bombers deep into enemy territory. The P-47, with its rugged construction and heavy armament, seemed perfect for the role. If it could survive its own dive performance, this is where Kartveli's design philosophy became critical. Other designers would have accepted the limitations, restricted the aircraft's dive speed, trained pilots to avoid high-speed maneuvers. Kartveli refused. He believed that if a fighter could outdive any opponent, that capability itself became a weapon, a guaranteed escape route, an offensive advantage, but only if pilots could survive using it. The solution would require understanding forces that operated at the edge of the known. In 1942, aerodynamicists understood the basics of shockwave formation. They knew that as airspeed approached the speed of sound, local airflow over the thickest parts of the wing could reach supersonic speeds, even while the overall aircraft remained subsonic. These supersonic zones created shock waves, sudden compression fronts where air properties changed dramatically. Behind a shock wave, the boundary layer, that thin film of slow-moving air clinging to the wing surface, often separated. When boundary layer separation occurred, the smooth airflow that generated lift and control surface effectiveness collapsed into turbulent chaos. On the P-47, this happened to the horizontal stabilizer and elevators. As the aircraft dove past approximately 500 miles per hour, shock waves formed on the stabilizer. The elevator, trying to move against turbulent separated flow, encountered forces measured in thousands of pounds. No pilot could move the control stick against that resistance. The stick simply froze, and the aircraft continued its death dive. What made the Thunderbolt different, what let Comstock and Dyer survive, was a solution Kartveli had built into the design almost by accident. The P-47's control systems weren't hydraulically boosted. They were purely mechanical, cables and push rods connecting the stick directly to the control surfaces. But Kartveli had included extremely effective trim tab systems on both the ailerons and elevators. Trim tabs are small surfaces, mounted on the trailing edge of larger control surfaces. When a pilot adjusts the trim, these tabs move into the airflow, creating forces that help position the main control surface. They're normally used for fine-tuning, reducing the constant pressure a pilot needs to maintain desired flight conditions. But in the compressibility dives, the trim tabs became something else entirely. They became the only way to maintain control when the primary surfaces locked up. Here's why it worked. The trim tabs operated through a separate mechanical system, usually a wheel or crank in the cockpit that mechanically drove a jack screw. This system had mechanical advantage, leverage that multiplied the pilot's force. More importantly, the trim tabs themselves were small enough and positioned such that the shockwave effects hitting the main elevator didn't completely eliminate their effectiveness. When Comstock rolled that trim wheel back in his dive, he wasn't moving the elevator directly. He was adjusting the trim tab, which created aerodynamic pressure that gradually pushed the elevator into the position needed for recovery. It was slow. It required patience in a situation where every instinct screamed to act immediately, but it worked. Republic's test pilots, once they understood the technique, began deliberately pushing P-47s into compressibility dives to map out the recovery procedures. The protocol that emerged was precise and unforgiving. At the first sign of elevator lockup, pull the throttle back to reduce speed. Do not attempt to use the control stick. The forces are beyond human strength, and the attempt will only exhaust the pilot. Roll the trim wheel back, moving the elevator trim nose up. Roll it slowly. Excessive trim will overstress the airframe when control returns. Wait. The aircraft will continue diving for thousands of feet while the trim slowly takes effect. As altitude decreases, air density increases. Higher density means the speed of sound increases, and the aircraft's Mach number, the ratio of its speed to the speed of sound, decreases. Around 15,000 feet, the shock waves begin to weaken. Below 12,000 feet, they dissipate entirely. Control returns gradually. Only then, gently, pull the stick back. Even gentle pulls create enormous G-loads at these speeds. Pull too hard and structural failure is certain. The recovery is measured in thousands of feet of altitude. Pilots needed to start the recovery process above 20,000 feet to guarantee pulling out safely. Start below that, and impact with the ground became likely. This was flying at the edge. This was survival through procedure, through understanding physics that most pilots would never fully comprehend. But it worked, and it gave the P-47 a capability no other fighter possessed. By December 1942, Republic Aviation had built this knowledge into training programs. New P-47 pilots underwent dedicated high-altitude dive training. They learned the signs of compressibility, the violent buffeting, the stick freeze, the Mach tuck that pitched the nose down even further. They practiced the recovery procedure in aircraft with experienced instructors, learning the feel of trim tab control, the patience required to let the procedure work. Some pilots died anyway. The learning curve was brutal, but the majority learned, adapted, and survived. Group deployed to England in January 1943 with the first combat P-47s. Their pilots knew something critical. They could dive away from any German fighter and survive. The Bf-109 and FW-190 could outturn them at low altitude. They could outclimb early model P-47s below 20,000 feet. But in a dive, the Thunderbolt was untouchable. Luftwaffe pilots learned this the hard way. A common German tactic against American bombers was to attack from above, diving through the formation, firing, then using the dive speed to escape before escort fighters could react. When they tried this against Thunderbolts, the German pilots discovered that the massive American fighters could not only match their dive speed but exceed it. P-47 pilots developed a tactic that became legendary, the bounce and zoom. Patrol at high altitude, 25,000 feet or above, where the turbo-supercharged Pratt & Whitney engine maintained full power while German engines gasped. Wait for German fighters below, engaging bombers or fighting other escorts. Dive at full power, building speed to 500 miles per hour or more. The shockwave buffeting was intense, the controls heavy, but pilots had learned to work through it. Make one high-speed pass through the enemy formation, guns firing in short, precise bursts. 8 50-caliber machine guns at 500 miles per hour delivered devastating firepower. Then, use the momentum from the dive to zoom back up to altitude. Any German fighter trying to follow couldn't keep up. If they tried to dive away, the Thunderbolt's superior dive speed meant escape was impossible. This tactic flipped the tactical situation in Europe. German fighters had to avoid diving when Thunderbolts were overhead. They had to seek different angles of attack, fight from below where the P-47's size and weight made it less maneuverable. The psychological effect was profound. German pilots who'd been confident in their aircraft's performance suddenly found themselves unable to dictate the terms of combat. A P-47 at altitude was a threat that couldn't be evaded through traditional fighter tactics. But Kartveli wasn't satisfied. The manual trim tab recovery worked, but it was complicated, required specific training, and still resulted in losses when pilots panicked or started the recovery too late. There had to be a better solution, and that solution would require thinking about hydraulics in ways nobody had attempted before on a fighter aircraft. The problem was force. At 500 miles per hour, the aerodynamic pressure on the elevator required thousands of pounds of force to move. Human strength topped out around 200 pounds of sustained pull. Hydraulic boost systems could multiply that force dramatically, but hydraulic boost added weight, complexity, and new failure modes. Kartveli had deliberately kept the P-47's flight controls mechanical to maintain reliability. Hydraulic lines could be shot out in combat, as many wounded P-47s proved when they limped home with dead hydraulic systems but functional flight controls. Yet, the dive recovery problem demanded a solution beyond pure mechanical advantage. In 1943, as combat reports accumulated from Europe, Kartveli and his team began exploring a hybrid approach. Not full hydraulic boost, which would make the flight controls dependent on hydraulic pressure, but something more subtle, something that enhanced control authority without eliminating the mechanical backup. The answer came from an unexpected direction, not from hydraulics, but from aerodynamics, and it would transform the P-47 from a dangerous beast that could kill its pilot into the war's most effective dive bomber. The breakthrough didn't come from Republic Aviation's main engineering department. It came from test pilots who'd been living with the compressibility problem every day, who understood viscerally what the numbers on paper couldn't capture, and it came from looking at the problem backward. Everyone had been focused on making the elevators work better at high speed. What if, instead, you prevented the aircraft from reaching those impossible speeds in the first place? Dive brakes weren't new in 1943. Dive bombers like the Douglas SBD Dauntless had used them for years. Perforated flaps that extended into the airstream, creating drag that limited dive speed during bombing runs. The concept was simple: increase drag dramatically, and terminal velocity drops. If you could keep a P-47 below 500 miles per hour in a dive, compressibility effects diminished significantly. Control forces remained manageable. The trim tab technique became unnecessary, but fighter pilots hated the idea. Dive brakes on a fighter? That was admitting the aircraft couldn't handle its own performance. That was accepting limitation instead of pushing boundaries. The whole point of the Thunderbolt's devastating dive speed was tactical advantage. Slow it down deliberately, and you surrendered the one capability that made bounce and zoom tactics viable. Kartveli understood the resistance. He'd designed the P-47 to be the fastest diving fighter in the world, specifically because that speed was a weapon. But combat reports were revealing something the engineering calculations hadn't predicted. Pilots were discovering that the optimal attack speed wasn't maximum velocity. At 550 miles per hour, the P-47 was impressively fast but also impressively uncontrollable. Small corrections were impossible. Gun tracking was minimal. Pilots blazed through their attack runs so quickly they barely had time to aim. Meanwhile, ground attack missions, which were becoming the Thunderbolt's primary role by late 1943, presented different problems. Strafing runs required precision. Rockets and bombs needed accurate delivery. Diving at terminal velocity produced impressive spectacle but mediocre results. Pilots needed to dive steeply to minimize exposure to anti-aircraft fire, but they needed controllable speed to actually hit targets. The engineering challenge was designing dive brakes that worked with the P-47's unique characteristics. Traditional dive brakes used hydraulic actuators to extend perforated plates into the airstream, but the forces involved at P-47 speeds were enormous. Hydraulic systems would need to be massive, adding weight that Kartveli's weight-obsessed design couldn't absorb without compromising performance elsewhere. The solution emerged through careful analysis of where drag could be added most effectively. Republic's aerodynamicists studied airflow over the Thunderbolt's large wing. The wing's undersurface, that broad flat area between the main gear wells and the flaps, offered significant surface area. If you could deploy panels there, relatively small panels positioned in high-velocity airflow, you could generate substantial drag without enormous hydraulic systems. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The challenge was deployment. At 400 miles per hour, the dynamic pressure, the force the airflow exerted on any surface, exceeded 1,500 pounds per square foot. A dive brake panel 1 square foot in area would experience 1,500 pounds of force trying to rip it off the aircraft. The actuators had to overcome that force to extend the panels, then hold them in position against continuous pressure that would bend or tear lesser mechanisms. Republic's hydraulic engineers, working through the winter of 1943 into 1944, designed a system that was simultaneously elegant and brutally strong. The dive brake panels, two of them mounted flush in the wing undersurface, were roughly rectangular plates measuring approximately 2 feet by 1 foot each. When retracted, they sat perfectly flush with the wing skin, adding no drag. When deployed, they rotated downward and slightly forward, extending about 6 inches into the airstream. The rotation mechanism was key. Rather than simply dropping the panels perpendicular to the airflow, which would create tremendous stress on the hinges, the panels rotated to a carefully calculated angle. This angle balanced drag production against structural loading. The panels created turbulence and drag without trying to stop the airflow completely, which would have been impossible at these speeds. The hydraulic actuators used a compound leverage system. The hydraulic cylinder didn't push the panel directly. Instead, it drove a linkage that multiplied force through mechanical advantage. This allowed relatively small hydraulic cylinders to generate the thousands of pounds of force needed to extend and hold the panels. The system ran off the aircraft's main hydraulic system, the same system that operated the landing gear and flaps. If hydraulic pressure failed, the panels automatically retracted through spring loading, eliminating one more way the system could kill a pilot. Testing began in April 1944 with a modified P-47D-30. The test aircraft, with dive brakes installed, was flown through exhaustive trials at the Army Air Force's test facility at Wright Field in Ohio. Test pilots took the aircraft to 40,000 feet and put it into maximum performance dives, deploying the dive brakes at various speeds and altitudes. The results exceeded expectations. With dive brakes deployed, terminal velocity in a vertical dive dropped from over 600 miles per hour to approximately 450 miles per hour. More importantly, the speed stabilized quickly. A pilot could roll inverted at altitude, pull into a steep dive, deploy the dive brakes, and within seconds, reach a stable, controllable dive speed. The elevator forces at 450 miles per hour were firm but manageable. No trim tab technique required, no compressibility buffeting, no locked controls. Just a steep, fast, controllable dive. The tactical implications were immediate and profound. P-47 pilots could now dive as steeply as dive bombers while maintaining fighter-level maneuverability. Ground attack accuracy improved dramatically. Rocket and bomb delivery became precise enough that experienced pilots could hit individual vehicles, gun emplacements, or buildings from steep diving attacks. The exposure time to anti-aircraft fire actually decreased because pilots could dive steeper and start their attacks from higher altitude. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Production P-47s with dive brakes began rolling off Republic's assembly lines in late 1944. The P-47D-30 and all subsequent models incorporated the system as standard equipment. Pilots who'd been flying earlier Thunderbolts without dive brakes transitioned to the new models and reported it was like flying a completely different aircraft. The confidence that came from knowing you could dive as hard as necessary and still maintain control transformed combat tactics. But here's what almost nobody understood, what got lost in the technical specifications and pilot reports. The dive brake system wasn't just about controlling speed, it was about rewriting the fundamental equations of high-speed flight. Kartveli and his team had done something that wouldn't be fully appreciated until jet aircraft began encountering similar problems a decade later. They'd solved compressibility not by fighting it directly, not by adding more power or stronger structures, but by controlling the boundary conditions. By ensuring the aircraft never quite reached the speeds where compressibility became catastrophic, they'd created a fighter that operated right at the edge of the transonic regime, that dangerous zone where subsonic and supersonic airflow coexisted, without crossing into the uncontrollable chaos beyond. This was systems engineering before the term existed. This was understanding that sometimes the solution to an impossible problem is changing what's possible. The P-47's dive brakes weren't a limitation, they were an enabler. They let pilots use the aircraft's tremendous power and weight, not to achieve maximum speed, but to achieve maximum effectiveness. The operational record proved the concept. Between D-Day in June 1944 and the end of the war in Europe in May 1945, P-47s flew over 546,000 combat sorties. They destroyed roughly 7,000 enemy aircraft in air-to-air combat, but their real impact was on the ground. Thunderbolts destroyed or damaged over 9,000 locomotives, more than 86,000 railroad cars, over 68,000 trucks, over 6,000 armoured vehicles, and uncounted fortifications, bridges, and supply dumps. These numbers represented Germany's logistics infrastructure being systematically demolished. Every locomotive destroyed meant supplies couldn't reach the front. Every bridge dropped meant divisions couldn't maneuver. The Wehrmacht, which had conquered most of Europe through mobile warfare, found itself unable to move in daylight without being swarmed by P-47s, diving from altitude with controllable precision. The dive brake system enabled this. Ground attack in a fighter requires getting low, getting slow enough to aim, delivering ordnance accurately, then getting out before anti-aircraft fire tears you apart. The P-47's combination of rugged construction, heavy firepower, and controllable dive performance created the template for what would later be called the fighter bomber, an aircraft that could fight in the air when necessary but specialized in destroying ground targets. Kartveli's design philosophy had proven itself. The P-47 was never the most elegant fighter. It was never the most maneuverable. It couldn't outturn a German fighter at low altitude or outclimb Japanese fighters in the Pacific. What it could do was survive, adapt, and destroy targets that other fighters couldn't effectively engage. The dive brake system was just one piece of that puzzle, but it was the piece that transformed raw performance into combat effectiveness. The human cost of developing these capabilities rarely appeared in official histories. Test pilots died working out the procedures for compressibility recovery. Combat pilots died when they pushed their aircraft beyond the limits, when they started dive recoveries too late or misjudged their altitude. The P-47 could survive mistakes that would destroy other fighters, but it couldn't make pilots immortal. One incident from March 1944 illustrated both the aircraft's capabilities and its limitations. Captain Walker Mahurin, an ace with the 56th Fighter Group, was attacking a German airfield at low altitude when anti-aircraft fire struck his P-47. The hydraulic system was hit, spraying fluid through the cockpit and starting a flash fire. The hydraulic pressure that operated the dive brakes, the landing gear, the flaps, all of it gone instantly. Mahurin's aircraft was effectively a glider with a still-running engine, but no way to control anything hydraulically powered. He couldn't lower his landing gear. He couldn't extend his flaps for a slower landing. And critically for this story, he had no dive brakes. Not that he needed them at that moment, but the hydraulic failure demonstrated the system's vulnerability. Everything that made the P-47 controllable, everything that let it operate at the edge of flight performance, depended on that pressurized fluid staying inside its lines. Mahurin, nearly blind from hydraulic fluid in his eyes, oxygen system destroyed, managed to keep the aircraft flying long enough to cross the English Channel. He crash-landed at his base with no gear, sliding the Thunderbolt across the runway on its belly. The aircraft was repairable. Mahurin walked away with burns and fluid-damaged eyes but survived to fly again. The incident highlighted what Kartveli had always understood. Redundancy and ruggedness mattered as much as performance. The P-47's mechanical flight control system meant that even with complete hydraulic failure, the aircraft remained controllable. The pilot lost the dive brakes, lost the landing gear and flaps, but the stick still moved the elevators and ailerons, cables and push rods, mechanical connections that enemy fire had to physically sever to disable. This redundancy kept pilots alive in situations where hydraulically dependent aircraft would have become uncontrollable. Yet, the dive brakes themselves, when functional, represented the opposite philosophy, using hydraulics to enhance capability beyond what pure mechanical systems could achieve. The balance between these approaches, mechanical backup for survival and hydraulic enhancement for performance, became the template for combat aircraft design for decades afterward. By late 1944, the war's momentum had shifted decisively. Allied forces were advancing from the west following the Normandy invasion. Soviet forces were crushing German armies in the east, and strategic bombing had devastated Germany's industrial capacity. The P-47 played its role in all these campaigns, but its design excellence became most apparent in the tactical details, in the individual missions where controllable dive performance meant the difference between success and failure. Consider the bridge-busting missions that became increasingly critical as Allied forces advanced through France and into Germany. German forces depended on bridges to move reinforcements and supplies. Destroying bridges required precision. Drop your bombs too early, they miss. Too late, you're too low to escape the blast. The P-47's dive brakes allowed pilots to stabilize in a steep dive at controllable speed, release ordnance at the optimal point, then pull out smoothly. The famous bridge at Remagen, the Ludendorff Bridge that became the first crossing point over the Rhine River, saw repeated German attempts to destroy it after American forces captured it intact in March 1945. Luftwaffe aircraft tried bombing it. P-47s flying combat air patrol intercepted them using dive tactics that capitalized on the Thunderbolt's superior dive performance. German jets, the revolutionary Me-262s that were faster in level flight than any piston-engine fighter, still couldn't outdive a P-47. The jets lacked dive brakes, lacked the refined high-speed handling that Kartveli's design incorporated. In a dive, they were as uncontrollable as early P-47s had been. This created bizarre tactical situations where obsolescent piston-engine fighters hunted cutting-edge jets by forcing them into dives. The Me-262, terrifyingly fast in level flight, became vulnerable in a dive because its pilots couldn't control the aircraft at those speeds. P-47 pilots learned to position above jet attack routes, wait for the jets to commit to an attack run, then dive on them from above. The jets could try to accelerate away in level flight, but that took time and energy. In a dive, the P-47 closed the gap and killed jets that should have been untouchable. These weren't common occurrences. Jet encounters remained rare through the war's end, but they illustrated how fundamental design decisions about control systems and high-speed handling created tactical advantages in unexpected situations. Kartveli hadn't designed the P-47 to fight jets. Jets barely existed when he drew the first sketches. But his obsessive focus on controllability at extreme speeds produced an aircraft that could adapt to threats its designer never imagined. The engineering legacy of the P-47's dive control systems extended far beyond World War II. When American aircraft designers began working on the first generation of jet fighters in the late 1940s, they studied the Thunderbolt's solutions to high-speed control problems. The F-84 Thunderjet, Republic Aviation's first production jet fighter, incorporated dive brakes as standard equipment, positioned almost identically to the P-47's installation. Kartveli himself led the F-84's design team, bringing forward everything he'd learned from the Thunderbolt program. The F-84's dive brakes operated hydraulically, deployed from the rear fuselage, and allowed the straight-wing jet to safely approach its Mach limit without the control problems that plagued earlier jets. This lineage continued through the F-105 Thunderchief, Kartveli's last great design, a supersonic fighter bomber that used sophisticated stability augmentation and hydraulically boosted controls to remain controllable at speeds the P-47 designers couldn't have imagined. Even modern aircraft, with computer-controlled fly-by-wire systems, owe conceptual debt to the P-47's solutions. The principle that you can control an aircraft's performance envelope by carefully managing its energy state, that you don't always need more power or stronger structures, but sometimes need smarter systems that prevent the aircraft from entering uncontrollable regimes. This principle traces directly back to those hydraulically deployed dive brakes on a World War II fighter. The production numbers tell their own story about the design's success. Republic Aviation built 15,686 P-47s between 1941 and 1945. That's more than any other American fighter except the P-51 Mustang. The Thunderbolt equipped 16 fighter groups in the European theater and served with distinction in the Pacific, Mediterranean, and China-Burma-India theaters. It flew with Allied air forces including Britain, France, the Soviet Union, Brazil, and Mexico. Post-war, P-47s served with air forces around the world into the 1950s. Some saw combat in the Korean War with South American air forces. The last combat P-47s weren't retired until the mid-1950s, a decade after the war's end. Remarkable longevity for an aircraft designed in 1940. But beyond the statistics, beyond the combat records and production numbers, the P-47 represented something more fundamental. It represented the moment when aircraft design stopped being purely about aerodynamics and power and started being about systems integration. The dive brake installation wasn't just a hydraulic actuator moving a panel. It was a carefully balanced system that considered aerodynamic loading, structural strength, hydraulic pressure requirements, pilot interface, failure modes, maintainability, and combat survivability. Every modern aircraft, from fighter jets to commercial airliners, embodies this systems approach. When engineers design a Boeing 737, they're not just designing wings and engines, they're designing integrated systems where hydraulics, electronics, flight controls, structures, and aerodynamics all work together as a coherent whole. That approach, that understanding that the whole aircraft is a system and every component affects every other component, that's the real legacy of projects like the P-47. Kartveli never became famous outside aviation circles. He died in 1974, his achievements known mainly to engineers and historians. No movies celebrated his designs, no dramatic documentaries traced to his personal story. He was an immigrant engineer who did his job with extraordinary skill and left behind aircraft that changed how wars were fought and how engineers thought about design problems. The P-47 itself largely faded from popular memory, overshadowed by more glamorous fighters like the P-51 Mustang and the Spitfire. Those aircraft were beautiful, graceful, the romantic vision of what a fighter should be. The Thunderbolt was none of those things. It was a massive, brutal, effective machine that did exactly what it was designed to do and nothing more. But in the details, in the engineering decisions about how to control a 7-ton fighter at 550 miles per hour, in the hydraulic systems that made dive brakes functional, in the careful balance between mechanical reliability and hydraulic enhancement, there's a story about how impossible problems get solved, not through single brilliant insights but through persistent, careful engineering that addresses each challenge systematically. The dive brake system on the P-47 wasn't revolutionary technology. Hydraulic actuators existed, dive brakes existed. What was revolutionary was understanding exactly where to place them, how to integrate them into an existing design, how to make them robust enough for combat operations, while keeping them simple enough for maintenance crews working on improvised airstrips. That's not the kind of innovation that makes headlines, but it's the kind that wins wars. In the end, the P-47's ability to dive at 550 miles per hour and pull out alive wasn't about one system or one innovation. It was about a design philosophy that refused to accept limitations, that looked at problems from multiple angles, that understood sometimes you solve impossible challenges not by fighting harder but by changing the rules. The trim tab recovery technique changed the rules about how pilots thought about control authority. The dive brake system changed the rules about what speeds were survivable. Together, these solutions transformed the P-47 from a dangerous beast that could kill its pilot into the war's most effective ground attack fighter, not because it was the fastest or most maneuverable, but because it was controllable, survivable, and deadly at exactly the speeds and altitudes where ground attack missions were fought. That's engineering excellence, not building the most impressive machine, but building the right machine for the mission. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.